record button.
There it goes.
Weird. I would have thought that Dirk and I would both have been hosts, and that either one of us could push the button, but apparently not. I pushed the button.
Okay.
I didn't realize it wasn't going. The icon on the screen makes it look like it's recording.
Yes. Okay. Then it's good that at least
it is now finally recording. Sorry for the delay.
Thank you. Okay, Hitoshi-san.
Okay, so anyway, who shared the slide? You shared the slide, or
No, you're running your slides yourself, so you should share your.
Control to share the slide is disabled.
Huh? So Dirk?
Yes?
I cannot share the slide.
Yes, you can.
Oh, no, I cannot.
You cannot?
It's disabled. It's disabled.
Okay. 1 second.
Okay.
Yep. Go ahead.
Can you see the slide?
Yes, we can.
Okay. Okay, just a moment. Okay, so this is Hitoshi Asaeda, and today's talk is related to our CCN info draft, and this is revision version 4, and we slightly updated the whole on previous versions. So this is a summary of changes. The first one is a node identifier. Actually, we previously assumed that node identifier can be an IP address, but according to the several comments, we changed the node identifier assumption from IP address to a node name, like a content name. The second one is about information reported in subblocks. In fact, it is not obliged for router to fill all data in subblocks. Because some router may not implement complex function to obtain the required data, and others may not want to disclose everything due to its policy. So, but it's not really, I heard it's not really clear. Can you see this, right?
Yes, they were gone for some time.
Okay, okay, so anyway, so we need to clarify that CCNF allows to omit complex function implementations. And the third one is regular interest and full discovery request. So we also clarify the regular request, which is default, and the full discovery request, which is optional. And there are several editorial collection and improvement. So the first one, node identifier. The previously in section 3.1.2 regarding report block, we said this field specifies the CCNF user or the router identifier. For example, IPv4 address of the incoming interface on which packet from the publisher are expected to arrive, or all zeros if unknown or unnumbered. Now we change this statement, this paragraph, to the following statement. This field specifies a node identifier, for example, node name or hash-based self-certifying name. Number 9 is actually the hop host draft, or order if unknown. This statement assumes that the name TLB defined in the CCNX TLB format can be used for this field, and the node identifier is specified in it. The next one is information reported in sublog. In section 3211, we clearly said, note that some routers may not be capable of reporting the following values, such as blah, 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 as shown in figure 15. Figure 15 actually shows the message format about reply sublog. And actually, as I said, some router does not have the capability of reporting these counters or values and so on, or some routers doesn't want disclose such kind of information. So these values therefore may be returned with null. We explicitly mentioned about it here. And regular and full discovery requests. So both are different, and we already discussed about some supportive mechanism, especially for full discovery request. And we want to keep the full discovery request as well, but the default is regular request. For the regular requests, in the regular request, the router forwards the request message upstream toward the publisher or caching router based on the fib entry, like the ordinary inter-data communications. So if the other protocol or mechanism, just they can work as a regular inter-data communications. So they don't need to have some special behavior for request and reply communication. But if the full recovery request is supported by router, then he needs to support various additional functions compared with ordinary CCN forwarder. So we explicitly say, unlike the ordinary inter-data communications in CCN, if routers that accept a full discovery request receive the full discovery, accept the full discovery request, the router should, so I need to modify the statement. The router should not remove the bit entry created by the full discovery request until CCNF repair timeout value expires. So this is a common, this is not a common behavior. So for the full discovery request, the router must support this special behavior. But note that full discovery request itself is an optional implementation of CCN info. It may not be implemented on router. Even if it is implemented on router, it may not accept the full discovery request from non-validated CCNF users or routers, or because of its policy. If a router does not accept a full discovery request, it rejects the full discovery request as described in section 311, and the routers that enable full discovery request may rate limit replies as described in section 10.8 as well. So we explicitly mentioned the difference of regular request and fully required request. So this is the conclusion. CCNX is compatible with CCNX version 1.0 TLB format, and it is a powerful network to providing various information in CCN. And CCNF implementation is already included in CCNX IETF 1.0 compatible forwarding daemon software named C4. So you can just download this open source, and C4 is a full scratch forwarding daemon, and CCNF is included as its unique tool. And as you see, that we need to revise several editorial changes. So we will submit the final revision in this week, I hope. And but the content itself should be feasible, and then I may ask the chairs to initiate a research group last call. Okay, that's all. Thank you.
Okay, thanks, Toshi-san. Just looking around, are there any questions?
I don't.
Okay, there's one from Colin.
Hi, Colin Perkins as an individual. I just wanted to check, it wasn't clear, what was the relation between this and the traceroute and ping address?
Well, maybe Dave can answer. Actually, the CCN info is a much more powerful network tool, and it's not just receive the network statistic data, and it can also observe the caching point and the various caching conditions, like a lifetime and so on. So it's a more rich network tool. But the implementation could be complex.
I think the mental model, Colin, is that CCN ping and trace route are like IP ping and trace route in terms of their capabilities, and that they're intended as not just the management but also an end user tool. And CCN info is more like SNMP to get to some MIB like things that are stored on routers forwarders. That makes sense?
Yeah, that makes sense, but it didn't necessarily come across from reading the drift.
Yeah, Hitoshi, maybe one of the things we could work on together is to, for both the CCN info draft and then the ping and trace route draft, cross-reference with, a sentence or two saying what the relative purposes of the work are, so people can go back and forth and see. That'd be a good idea to do as part of a version that goes to the last call.
Yeah. Okay. Sounds good.
Yeah. Okay. And I'll point out that we haven't had nearly enough review on ping and trace route for them to be progressing very far yet. So CCN info is what we're focusing on for now until other people want to catch up on the other work.
Okay, I see. Yeah, I agree.
Okay, any more questions? Okay, then let's clarify this with the next revision. Hitoshi, thanks a lot for the presentation. And we're now moving to the ICN LoWPAN update by Zheng. And
yeah, all right. So I'm not able to share currently.
Yeah, just a second. WebEx, come on. Hitoshi, can you stop sharing your?
Okay, just a moment.
Ja, bei mir geht es jetzt los.
So Dave, maybe you can take away the printer role from Hitoshi. I can't do it.
Okay, I try to quit.
Okay, that was brute force. So Cheng, I cannot make you presenter. I don't know what's going on here. Dave, can you try? Dave, can you try to make Schenk presenter? The WebEx doesn't allow me to do it.
I can't even see him in the list of participants in the permissions list.
That's strange.
You can see Thomas. Toshi, Colin, Daniil.
This is quite
He's not
broken.
even in- he's- Let's see. Yeah, he shows up in the regular participants list. But not in this list.
Uh-huh.
So should I try to rejoin?
No.
Just a second.
According to my thing, all participants have the privilege to share documents.
So Jen, can you try again? Something has changed now.
So the button is still green. I can't click on the
Ah, come on.
share button. Gray.
Try the menu share and say share content or share whatever.
I have to drop the ball onto them to let them present. Nope. Oh no. Application.
Yay!
Okay.
All right. Can you see my slides?
Yes, we can. Thank you.
All right. Thanks, Dirk, Dave, for the introduction. So my name is Cenk, and we have like the 7th iteration of the ICN draft. And here are basically we have like 4 little amendments to the draft from the 6th iteration to the 7th iteration. They are kind of small, so thanks to Colin, who pointed out that the RFC 5743 actually like demands to have like various notices in the abstract and introduction to identify this draft as a product of the IETF. So we added a couple of notices there. And then in section 411, which basically describes how we allow extensions for dispatches, for example, in future drafts. And there we added a paragraph that future drafts should use like structured manifests, like for example in the flick draft, and we also put a link to the flick draft here for the exchange of configuration parameters. And then the 3rd amendment is that, again, thanks to Colin, we added like some information about which experimental evaluations could be interesting for future evaluations and how they would be fruitful for the ICN open work and how to advance in this direction. So we added a couple of paragraphs there. And then last but not least, we added the IANA consideration section, and we basically did replace all and added a to be defined text blocks in the document where we used like the numbers. And then the draft itself was sent to IANA by Colin 7 days ago. And basically we are now waiting for the response, and depending on the response, then we would either need to update the IANA code points or the document will be sent directly to the ISRG for review. And that's the update. Very brief. Thanks a lot.
Thank you, Cenk. Colin is in the queue. Please go ahead.
Hi. So I haven't had a chance to share the response I got from IANA yet, but I will do so either later today or tomorrow. The feedback we got from the from the designated expert was that it seems to be consuming a lot of code points, and they were wondering if it was possible to adapt the format to use or less of the IANA registered code points.
as I say, I'll share the details of that as soon as I can.
All right. I think we have to look into that then.
Okay, thanks, Colin.
Some discussion to be had, clearly.
Yeah, okay. So just quickly, Marie-José, again, sorry. It's great to hear you typing so actively, but I just had to mute you. Sorry. Okay. No further questions. Then yeah, let's move on, Cenk, with the time TLV update.
Okay. Let's switch the slides. Here we go. Do you see the slides?
Yes.
All right, thanks. So in this particular draft, we talk about time, like a compact time representation in the CCNX protocol, especially for the interest lifetime and the recommended cache lifetimes. First, we had a version bump a couple of weeks ago from 0.0 to 0.1, and we had a major change in section 4, which talks about how we do the the time encoding. And basically, we are now using the formula that is based on the IEEE 754. This is the floating point specification, and thanks to Mark for this hint. And we added a couple of numbers, like sample values, to see which values we get from the compression, or which values are allowed to use. So the compression itself uses an 8-bit timecode. So we have 8 bits, and then out of these 8 bits, we define 5 bits for the exponent and 3 bits for the mantissa. And I will show you why we took these values later. And we have 2 formulas. And again, these are basically the same formulas taken out of the IEEE 754 specification. The upper formula is for subnormal numbers. This is if you have like an exponent of 0. We use the upper formula, and if you have an exponent out of the blue range greater than 0, then we take the second formula. And the idea of having a subnormal range is that we close the gap between 0 and this lowest number that the lower formula can show. So, and just a quick idea of why we took these configurations. I will now show you sample configurations. And we will see how they perform. Here in this graph, you can see on the x-axis the time code. So I said we have 8 bits, so we go from 0 to 255. And on the y-axis, we have the time in seconds. So if you look at the configuration 350, which means we have 3 bits for the exponent, 5 bits for the mantissa, and 0 is a bias that you can apply to the formulas, to the values itself. And in this configuration, we can see, okay, we have the red dots, and everything like between the red dots is the mantissa or the precision itself. And every time we encounter a dot, we have a mantissa overroll, so we increase the exponent. So we can see we have a fairly large precision here, but the range itself is really low. We only touch close to 1,000 seconds here, which is not enough for our use cases. If you look at another configuration, which is 440, so 4 exponents for mantissa, we can see that the precision itself is halved. So we have less precision, but the range is much higher. So we can almost get 10 to the power 5 seconds here, which is a little bit more than a day, but a day is too less for our use cases. So we go one further, and we have 5 exponent bits and 3 mantissa bits. You can see that precision is again much lower, but we reach in this case a huge range. I mean, this is basically 120 years we can represent this configuration. But then again, do we really need these high numbers at the lower end? And maybe we should concentrate more on the lower end. And this is what the bias is doing. If you apply a bias of -5, this means we divide all values by 32. you can see the new configuration is just Y shift on the Y-axis down, so we have a lower range, but we have more values than the lower end we can use. And with this configuration, we have a sub-second, we have millisecond resolution on the lower ends, and we go up until 4 years. We can reach 3 to 4 years at this configuration, which is fairly enough for interest lifetimes or recommended cache times. So there was another update in the draft, which handles the protocol integration. So we have this time, the compressed time coding, but how do we use this in the ICNRG protocol itself? And we said that we will now concentrate in this draft only to the interest lifetime and the recommended cache time, which of course has the effect that the RCT, the recommended cache time, is currently it is an absolute time representation. It's the milliseconds since epoch, Unix epoch, and it's an absolute time. But if you want to use this, then we have to make the RCT a relative timestamp. So, then we say in the draft, if we use the compressed time, then RCT becomes a relative offset. And currently we say we opt for the solution that we say if the TLV length of RCT or interest lifetime is 1, the 8 bits, then we say we use the compressed time. If it's anything else, then we use the same specification that is in the ICNRG RFC. And here are alternative integrations. So instead of using this trick above, setting the length or looking at the length, we could also go with nested TLVs, which obviously have the the pitfall that we introduce overhead, which is especially in the IoT case not desirable. Or we could define new top-level TLVs, which have, for example, interest lifetime compressed. Could be that kind of a variant, and we could say, instead of interest lifetime, we use interest lifetime compressed. The next steps for this draft are to further discuss this protocol integration. We didn't get much feedback yet, but I hope that people have more ideas on what would be the best way to integrate this code points or the compression into the ICNRG. And then we have received a lot of feedback from Mark regarding how to improve the draft itself, and he recommended that we put all time values we can represent with this configuration to the appendix as a table, a huge table, and also to provide a pseudo algorithm how to convert from time seconds to the compressed time and backwards. Yeah, all in all, it's actually a very simple draft. It's not that long. And the question would be, are we ready to adopt this as a research group item or not? Thanks.
Yeah, thank you, Cenk. So before discussing that, maybe are there any technical questions? Okay, I don't see anything. Yeah, so just to make everybody aware, so this would be, say, the first update of the ICNRG RFCs that were published earlier. And so in that sense, so we think it's probably the right thing to give control to the research group and adopt this draft eventually. Is there any opinion, any feedback on the question? Okay, then what we'll do is we'll ask that question again on the mail list. So the chairs are leaning towards adopting this, but yeah, let's see whether there are any other opinions. Thanks a lot, Cenk.
Yep, thank you.
And now we're on with Dave on reflexive interest forwarding. And Dave, are you still on the call?
Sorry, I was muted. I'm trying to figure out how to get a PowerPoint directly shared. Share content, share file. Sound right. Here we go. Loading file. Loading file. Loading file.
Yeah, looking good.
So while it's loading the file, let me get started. So this work grew out of some ICN research that the team that Dirk and I and a bunch of other people have been on for a number of years, looking at how to apply ICN in environments other than simple content retrieval. And whether these types of protocols actually are a good way to do things like remote procedure calls and sensor networking and other sorts of more computationally focused uses than just simply ask for some data and get it back. All right, how do I drive this? There we go. So the way the talk's going to go is I'll talk a bit about the motivations for why one might want to use multi-way interaction rather than just simple request response in ICN. People have tried to do this in the past, so we'll go over some of the problems with the approaches people have tried in the past. Then I'll introduce this design that we have for this facility called reflexive forwarding. Talk a bit about the use cases that we think this applies well to. And depending on how well things go, if there's time, we'll talk about some of the other things in the draft in terms of implementation and operation and security and privacy. So some of the motivations for doing this is applications often need multi-way handshake. So things like any type of RPC or remote method invocation, not only do you have to invoke the method, but somehow the arguments have to make it from the client to the server. You have to have some way to perform authorization of the clients. And in some cases, particularly for long-running computations, you'd like to separate the invocation of the computation from the return of results. Second motivation is that you'd really like some way for sensors and actuators. Why did this go backwards? Somebody did something with my slides. Okay, here we go. All right. They moved themselves amazingly. All right. For sensors and actuators, we'd really like to see a way the data can be fetched from the sensors rather than just pushed. That so that sensors don't have to be constantly waking up, and that people who need the data don't have to constantly pull the sensors in order to get it.
So, Dr. Dave, sorry to interrupt. There's something wrong here with the slides. We still see the title slides. They're not really advancing.
I advanced it. It's showing right on my screen. Let me advance and go back.
Everyone has to advance, I think.
This is weird.
Right. So the viewer can advance themselves.
Wow. Why is that? Shall I try a different sharing way of doing this?
Yeah, with window sharing and everything's different.
All right, let me try that. There. Oh, great. That's grayed out. Won't let me do it. Do you want clearing this time? Remove content. Yes. Well, no, wait. Yes. No. All right, now share. Well, now it's all grayed out. I can't share anything.
Let me see what I can do.
I'm sorry, guys. My old company that produces this software.
Dave, sorry, do you have an option to share PowerPoint as an application?
I don't see it. I don't see.
There's a button at the bottom right next to the camera for sharing, and you should have an option to share PowerPoint.
Really? All right, let me try it. There's a button down.
Yeah, if you look where the buttons are for mute, for camera,
Yeah,
and
I have such a button, and it says share file or new whiteboard.
Okay, it may be a macOS privilege thing that you cannot share Windows on desktops. Then I guess that's the only way we can do it. Oh, I can share slides.
Yeah, why don't you do that?
Yeah, 1 second.
Why is that? Are you not on macOS?
I am, but it's probably a configuration thing. One second.
Share content. Yeah, the only options are share file or whiteboard.
yeah, I see that now. That's strange.
Data tracker slow. Okay. Okay, we're back.
By the way, you're the host now, right?
I hope so. Okay.
Okay.
Can you see them?
Yeah. All right. So third slide. Next slide. Right. And then I was on the last bullet of this slide to say that there's all kinds of cases where you need some type of peer state synchronization. This is obviously well known because transport protocols provide three-way handshakes, and other protocols like for establishing multimedia sessions need multi-way handshakes. Next slide. Hello?
Yes.
Next slide, yes. Okay. So people have tried to do these things with NDN and CCN in the past, but there are sort of like two classes of problems, one of which is that people wind up pushing a lot of data in interest messages. And that, when they get really big, you might even need fragmentation of interest. Of course, it gets pretty ugly since it has to be done hop by hop, and you need complicated and robust fragmentation protocols. And it also messes up a fairly deep assumption in the existing protocols that interest messages are small, and congestion control protocols that people have designed for ICN definitely try to exploit that. And when the interest messages are no longer small, congestion control gets messed up. The second is that if you're going to put important data in these messages, you're going to need to sign them, or the guy on the other end isn't going to believe the data in the interest message. So that makes it even bigger. And of course, now it shifts the computational cost onto the producer to check the signature before it does anything with this data. And then lastly, if the computation or whatever is happening as a result of that interest gets abandoned for some reason, you've wasted all the bandwidth to push all that data. Next slide.
Yep.
The other thing is, given that the protocols are independent two-way exchanges of request and a response, if you have to construct a multi-way exchange out of these independent two-way exchanges, where the exchange is going in, one of the exchanges is going in the opposite direction, now somebody who's a consumer, with the assumption that consumers have certain anonymity properties and initiator properties, now consumers need a routable name prefix so that the independent interaction coming in the opposite direction can reach it. This has a number of bad effects. It exposes the consumer to potentially unwanted traffic, puts burdens on routing to propagate the routable name prefix far enough to reach this producer. And in mobile environments, where ICN has been touted as having sort of like natural consumer mobility, but has complexities if you need producer mobility, now all the consumers also become producers, and they need the producer mobility machinery to be operating for them as well. Another problem, of course, is that the consumer, in these cases, gets to choose the name it wants to be reached by. And as we've seen in many cases, like FTP and other things in the IP world, if you allow a user to assert a name and hand it to a second party, expecting that second party to use that name, this opens up gigantic reflection attacks. Where a consumer can cause a producer to mount a reflection attack against anybody whose name they can construct. And then lastly, just from a state machine point of view, correlating independent exchanges can be very error-prone. And as we've seen in the case of key exchange protocols, this can be, of course, catastrophic. And for protocols like multimedia, any of you who have lived in the world of SIP and SDP understand that getting the synchronized state machines of SIP going in one direction and SDP offer answer going in the other direction has been just a horrible mess for 10 years. Next slide.
Yep.
So instead, we are extending the two-way exchange of NDN and CCN to allow for a reflexive exchange going back in the direction from the producer to the consumer. And this turns out to be quite easy because we can utilize the existing PIT breadcrumbs that are established by the interest sent by the consumer to the producer, which has enough state, obviously not just for the returning data message, but to allow an interest message flowing back the other way to reach the consumer without having more routing information. So we've defined a scheme called reflexive name prefixes, which can be seen and understood only by those already in the established consumer pairing. Sorry, pairing is that has been established by the interest. We also provide a fib enhancement so that when these reflexive interests coming back the other way arrive at a forwarder, it can use the existing forwarding machinery to get it back to the consumer. It doesn't need a super special code path to do that. And lastly, it directly couples the state of the original interest data exchange with the reflexive exchange. So the state is easy to map correctly, both at the consumer and the producer, and unwound properly there and at the forwarders when the final data message comes back. Next slide.
So Dave, your audio is almost fading. I think you need to stay close to your microphone.
I am close to the microphone.
And not change the distance.
All right. I'm getting even closer. Now, this slide had a really nice animation, so if I'd been able to use PowerPoint, it could have all been a lot easier to see. But I'll walk you through it very quickly. So if you work top to bottom with the consumer forward and the producer, the consumer issues an interest message with its name, called a T, being a certain producer, and includes an extra field in the interest message called the reflexive name prefix, which has a value of, noted here, of X1. I'll talk in a minute about how those values are. This creates two pieces of state in the forwarder, creates the normal PIT. It also creates a special fib entry, which points back to the face that the interest arrived on from the consumer. This then arrives at the producer, who can create the state that's used for its normal exchange, but also has some state that it can use to construct these messages that are reflexive going back the other way. So this shows one instance of a reflexive interest going back through the same forwarder, creating a PIT entry, and reaching the consumer. The consumer does what he does with it. He creates a data object that responds to that interest, or has it already created from an earlier computation, returns that in a data message, which comes back, consumes that PIT entry, reaches the producer, and then the producer completes the entire exchange with the original data message. So what we have here is normally a four-way handshake, and it could be turned into a three-way handshake if the application doesn't actually need the final leg of the exchange. Next slide.
Okay.
So the machinery for this is relatively straightforward. We define a new name component type, and remember, CCN has all along had type name components. NDN originally had some syntactical conventions for names, and now also has explicit name component types. So we define a new one, which then has to be the high order name component for any of these reflexive names and used to form the name prefix. Its value is a 64-bit random number. Chose that to have enough entropy so that you can identify the consumer with high probability for the duration of an exchange, actually much longer than the duration of exchange, certainly for the duration of any reasonable exchange. And since we use a different value of this for each initiated intrastate exchange, this limits any kind of linkability you can get from reuse of these identifiers. So you can construct a variety of different interaction capabilities from this. The name prefix can actually be of a single full name of one object. It can be a prefix out of which the producer and the consumer can name multiple objects. A good example of this is arguments to functions or remote procedure calls, where the actual suffix names are known a priori through the interface description of the procedure call protocol. Or it can be the full name of a flick manifest. So if you need to fetch via reflexive interest a number of objects, you can place those in a manifest. Next slide. So what does the forwarder do? The forwarder creates and manages short lifetime fib entries for any of these name prefixes that are in an incoming interest. They'll query those fib entries and no others if an interest arrives in the first byte name prefix. This is very easy. It's a one-byte check so that you don't have to traverse a full longest name prefix match style fib entries for those things. And you'll see in the next talk on the NIST forwarder, there's some ideas they have for how to make that just as efficient as any type of hash lookup. And then this fib entry is consumed along with that fib entry when the data method is by the producer. Next slide. So let's go through some use cases, because I think if you don't believe these motivating use cases, this is a lot of change to the architecture to introduce for no good reason. So we'll walk through three use cases. Let's start with remote method invocation. Next slide. So historically, what happened was a couple years ago, a bunch of us defined a whole protocol for doing remote method invocation using ICN. And in the process of doing that, part of the work was in fact to create a reflexive naming scheme and a reflexive interest scheme. And though this spec is slightly different from what we actually implemented back then, the design is shall we say, aesthetically identical to what we had done there. So we use for remote method invocation, this is used for retrieving authentication authorization information from consumers, so it doesn't have to be pushed. And a producer who doesn't want to talk to a given consumer can refuse to even ask for that information, or if it asks for it, it can look at it as data messages, which are correctly encrypted and signed, and for fetching the arguments to the method calls. And you can complete this either immediately, once you've fetched the arguments and done your authorization, by returning the result in the returning data message, or as Rice potentially can do it, by returning a name call of a func, which is a handle on the result, so that the consumer can later poll for the result, and if there's a long-running computation. Next slide. So this shows, for example, the operation of a single remote procedure call with two arguments. So the first interest message invoke tries to invoke it. The producer then goes and issues two reflexive interests to fetch the arguments for the function. excuse me, those come back. And only at that point does the producer need to commit any resources to the computation, at which point it can return a func name to the consumer, perform the computation. The consumer, after waiting a while, there's a way to, in the func to say how long the consumer should wait to ask for the result. It issues an independent interest to fetch the result, which then comes back. So that's how reflexive interests are used for remote invocation. Next slide. So a number of papers in the early time of ICN pointed out that for RESTful web interactions, often the request message in HTTP is bigger than the response. Papers published that showed that the asymmetry can be quite dramatic. So what we'd like to do is, again, keep the request small by only placing the actual URI for the request in the interest messages, then turn around and get all the parameters, including any authorization via reflexive interest, and all the HTTP goop, cookies, accept foo headers, all the other stuff can be retrieved with a pull from a reflexive interest, returning the data via a regular data message. Now this, obviously, compared with HTTP, in theory, gives you an extra half round trip that otherwise wouldn't be needed. But then if you look at how HTTP actually runs over QUIC or HTTP, there are going to be multiple round trips due to TCP ACK anyway. Next slide. A third, I think, fairly compelling use case is to convert sensors from push devices to pure pull devices, such that sensors only need to act as a consumer. They can wake up on a timer or event of new data being available and issue an interest message, which is effectively a phone home call to an application gateway or an NDN repo type of element. This, in turn, provokes a reflexive interest data exchange initiated back from the gateway toward the sensor. Now no longer needs a routable name prefix or any of that stuff. And the data can either be sent back directly as a data message to the gateway, in which case the gateway then has to construct its own data object out of that, sign it. Or if the sensor is capable of doing so, naming, encapsulating, and signing the data itself. Either of those two schemes work. I'll point out that in a lot of IoT applications, people care perhaps more about the identity of the gateway than they do about the identity of the sensor. And hence, it's perfectly okay for the gateway to repackage the data coming back as an ICN data object with a name relative to the gateway and sign and encrypt it there. Next slide. So here's the example protocol ladder. The sensor can wake up. He issues a phone home to the gateway as a producer who forms a reflexive interest requesting the associated data. Goes back to the return. Data is returned and the data result is stored. And either you can complete a four-way handshake or you can just let the interest time out. In the draft, there's some suggestions about what interesting information could in fact be returned by the gateway to the sensor. Things like perhaps how long to wait to wake up again, and also the ability to keep time synchronized correctly with sensors that have clocks that drift. All right, next slide. How are we doing on time? I haven't been keeping track of my time. Guys, sorry, I haven't been keeping track of my time. Hello, hello?
Yep. So can we speed up a bit so we have enough time?
Well, I don't need to get through everything. Let me talk just a bit about some of the implementation questions, but go read the draft because it's very hard to summarize a lot of the stuff that's in there. So for forwarders, if you have a low-end device that's only going to be forwarding a few thousands or tens of thousands of interest per second, you don't really need to worry about this. Very straightforward implementation techniques will do the job just fine. But for a high-speed forwarder, we're about to hear about one in a minute, you have to be very, very careful about both memory access. And one of the things that this changes is the assumption that we have in high-speed forwarders previously that fibs were almost all read-only or read mostly. And now we have something that can update the fib effectively at the rate of arrival of interest. So you probably don't want to use the same fib data structure that you do for your regular fib for these. So the draft recommends a particular way to do a separate fib called an RFib that just uses a straightforward, really fast hashing algorithm in order to get the data. And when I looked at the slides on the next talk, you'll see there's another scheme there that looks kind of nice too. Also, when handling interest, high-speed forwarders in general don't have a PID as a global data structure. They shard it in some way. So if there are any operations from reflexive interest that require either lookups or even worse, updates across shards, that can be really tricky. So there are two ways in a high-speed forwarder to deal with this. One is to just avoid cross-shard updates entirely, or keep them as low frequency as possible, or come up with a different scheme on the input side to force reflexive interest into the same shard as the original interest. Next slide. There's also some interesting interactions with interest lifetime, because it's generally very hard for a multi-way interaction for a consumer to actually pick a good interest lifetime. So the draft suggests some ways that forwarders could arbitrarily inflate interest lifetimes to account for the there's a proposal for how to do that in the spec, which also has some complications for high-speed forwarders, which in turn are also talked about. Lastly, interest aggregation is one of the big bugaboos of these architectures, and one piece of good news is that this all seems to work just fine with interest aggregation. A reflexive interest prefix is just another one of those fields in interest, which causes you to not be able to aggregate interest. You create a separate fib entry. Next slide. For consumers, the consumers change, because instead of having these independent data exchanges and constructing names, you have a different sort of API and interaction for multi-way exchanges with the rest of the system. The choices that a consumer has is when it responds to a reflexive interest I already sort of mentioned, which is you need to use a plain data message if the lifetime of what it's returning is meant to stay inside the single interaction, or you can encapsulate a whole data message with its own name. If you're returning data whose lifetime is meant to survive beyond the existing exchange. And then you set the other fields appropriately for the data. I won't go into those details. There is one additional complication, because the state is in the forwarders for the producer to bombard a consumer with reflexive interest. It's nice for the consumer to be able to stop that if a producer is misbehaving, and there's a way to do that. Next slide. So I'll end with one piece of pretty bad news. This is not backward compatible, since you need an unbroken chain of forwarders to support this, or things don't really work very well. So we suggest three possible ways to overcome this backward compatibility problem. One is to ignore it, which I describe how you might get away with this, but don't really recommend that is the best way forward. We could bump the protocol version number, which deals with it very nicely. Anybody adding that TLD would have to bump the version number, and then back forwarders would just reject the interest. So that's really simple, but it's a really big hammer. And we want to think carefully before we pull that big hammer out. And then the third, which is my personal favorite, but also the hardest to accomplish, is let's create a capabilities exchange protocol so forwarders know the capabilities of the next hop, so they can decide whether to forward something on the next hop or not, depending on the capabilities of that next hop. But that, of course, requires a whole new set of work to construct such a protocol. Next slide. I think we're about done. The protocol encoding changes, that's the simplest part of the whole thing. It's one new TLV with a TLV type. and a 64-bit integer. Next slide. So for security, I think it's important to point out that one of the big motivations for doing this work in the first place was to improve security. And it's motivated by improving both security and privacy by avoiding payloads and interests that have to be signed, all the associated vulnerability or computational attacks on producers. It avoids routable name prefixes for consumers so they aren't exposed to attacks of various sorts. And it avoids sending names that can be crafted by consumers to producers, which can open up reflection attacks. So we view this as actually an improvement to security over the existing ways people have tried to make these capabilities happen with ICN. Next slide. So a few things to consider. One needs to at least talk about the possibility of collisions on reflexive interest name prefixes. This is easy to deal with if you happen to have a crypto quality pseudo-random number generator, and we basically say, yeah, you have to have one. You're going to need one for your crypto algorithms anyway. So just ensure that your 64-bit random values are actually produced by a crypto quality random number generator. These do produce extra resource pressure on the PIT and FIB, so they're more expensive on compute and memory. So you may need some resource allocation algorithms in your forwarders that put these in a separate resource category so they don't overrun simpler requests. And lastly, from a privacy perspective, we're in the same world of privacy is hard for ICN protocols because they leak names. And this is no different in that regard. We don't think it makes it any really worse because the names are only exposed on the path back to the. On the other hand, the use cases we're proposing have interaction patterns, which says that a surveillance attacker can observe the interaction pattern either through timing or message capture, and potentially produce linkability information just based on the interaction pattern. Now, this would obviously be true even in the absence of reflexive forwarding. It's only to point out that if you start using ICN for these more complicated multi-interaction use cases, those interactions have patterns that can be detected by surveillance and produce linkability. And I think I'm done. Next slide, I think, is the final slide. Yep. Okay. I'm done. Thank you for your time.
Are there any questions? Yes, there's one by David.
The RMI example, you had multiple reflexive interests. I think there was a slide example. How can you send multiple reflexive interests for one exchange, for one outer exchange?
Well, remember, what's sent from the consumer to the producer is the first name component, which is just a prefix. So the producer can add suffixes to that to retrieve as many data objects as it needs to, or add a suffix for a flick manifest that then returns other things and initiates more reflexive interest exchanges.
Okay. So from a previous slide, I thought the reflexive prefix, whatever it's called, was consumed once the first reflexive comes.
No, it's only consumed by the final data message going back.
Okay, thanks.
By the way, if there's something in the draft that isn't clear on that regard, please review it and send me comments. I mean, this is, a zero, well, there's a 0-1 out because I worked with Ken Calvert on a bunch of stuff that really, I think, improved a lot of the exposition. But again, this is fairly preliminary work, and it needs a lot of review and thought by people. We're going to continue to work on it if there's interest in the RG.
Okay. Cedric,
thanks everybody.
Cedric is on the queue. And Dave, you really have to mute your mic while someone else is talking.
I was just curious what happens to those entries in the bit if you just do a three-way handshake. Do you leave them timeout, or are they open for anybody to use? And what's going to happen to that? You had this, like in the early slides, you were talking about those. You were showing a four-way handshake, but you said that, oh, but it could just be a three-way handshake if we don't send the last message. I was curious what kind of percent. Can I use those?
Well, it just times out like
data.
It just times out like any other interest data exchange when you don't respond to the interest. I don't actually recommend that for almost any of these use cases. But some people, there may be cases where the cost of the extra bandwidth to send the final response is sufficiently high compared with the cost of keeping the state until it times out, makes the trade-off in favor of the timeout. And you can decide one way or the other depending on what your use case or application is.
Okay, I'm closing the virtual line here because we really have to move on.
Just real fast, hey folks, if you have more questions, just fire them off via email on the list to me, and I'll try to be responsive and answer them.
Yeah, so we'll be running a bit over time today. I hope so, not a big problem. So next is Jun Xiao with a presentation on an NDN DPDK forwarder.
I think the host has to share the slides.
I can make you presenter. Let me.
Okay, that's better.
Now it should work. You try.
Yes,
yeah.
you can see it. Okay.
Yes.
I am Jun Xiao. I'm a member of National Institute of Standard Technology, and today I am presenting the NDN DPDK forwarder. NDN DPDK is an NDN forwarder over native Ethernet without using any overlays. Our goal is line speed forwarding on commodity hardware, and so far we have achieved 106 gigabits per second between two ports. The forwarder's design has a parallel architecture so that we can use multiple CPU cores to process traffic. The forwarder has efficient data structures in pre-allocated memory pools. Then by using DPDK, the data plane development kit, we can use the user space PCI drivers with hardware offloads. Also, we are designing disk-based caching on NVMe drives, and we are investigating the potential of FPGA acceleration. This diagram shows the architecture of the forwarder. It's divided into 3 stages. Each are some threads or pinned to CPU cores. On the left side is the input stage. The input thread will receive packets from the hardware Ethernet interface and decode them, perform NDN-LP reassembly if necessary, then determine which forwarding thread should handle them by doing name lookups and other dispatch methods that I will explain later. In the forwarding stage, the forwarding thread implements the NDN protocol. It will process interest data and the NAC packet according to the protocol. And each forwarding thread, it has a PIT and a CS composite table, and it has the fib. And there are also crypto helper thread and the disk service thread to assist the forwarding threads. In the output stage, output thread will perform packet NDN-LP fragmentation if necessary, then schedule the packets for transmission onto the Ethernet adapters. First, I explain how the fib works. The fib lookup, we use 2-stage longest prefix match algorithm. This algorithm is inspired by a ANCS 13 paper named Data Networking on a Router, Fast and DOS-resistant Forwarding with Hash Tables. Other than that, I designed the rest, which are the new things. So the management, if management wants to update the fib, like insert or remove next hops, it needed to do it through RCU read copy update. This is to achieve thread safety. Then each fib entry has a pointer to the forwarding strategy. Forwarding strategy is a function that it determines how to forward the interest. And the strategy will have opportunity to observe when the data comes back and then store the measurement such as round trip time of each next hop. The measurement is stored on the fib entry and therefore the measurement granularity is the same as the fib entry. When strategy needs to update a fib measurement, it can do so without going through RCU for efficiency reasons. But this also means each forwarding thread needs to have its own fib partition so that multiple forwarding thread or multiple strategy cannot update the fib entry at the same time, which would be unsafe. For the PIT, we have PIT sharding. Algorithm. So each forwarding thread has a private PIT instance. The PIT itself is a hash table, and it's implemented with non-thread safe data structures, which is somewhat more efficient than the thread safe counterpart. But because of PIT sharding, there are two requirements on interest dispatching. First is two interests with the same name. They must go to the same PIT because this is required for interest aggregation. The second requirement, if their multiple interests has the same name prefix, not the same name but sharing the prefix, they also should go to the same PIT because this is needed for effective strategy decision since the forwarding strategy operates on namespace granularity. They collect a measurement like that. So the solution is we dispatch the interest by the hash of its first two name components. So this is how it works. We have in the input thread, we have the name dispatch table or NDT. NDT maps from the hash of name prefix to a forwarding thread ID. NDT is thread safe. It is an array of atomic int, and because the map key is the hash, so many name prefix would share the same entry. In the input thread, when the interest comes in, the input thread will compute the hash of first two name component. Of course, the number is configurable. Then using the hash value, it will take the lower usually, suppose the NDT is 64K entrance, then it will take the low 16 bits of the NDT. Of the NDT index, then it will find where that entry is. If that inside of that entry is a forwarding thread ID. So in this example, that the NDT entry says the name prefix corresponding to forwarding thread 1, so it goes to forwarding thread 1, and then the interest goes into that PIT. This kind of PIT sharding, it also has implication on data dispatching because data and the NAC must go to the same forwarding thread that forwarded the interest, since other PIT do not know about the interest. Normally, I could use the same name bit dispatching algorithm, but there is a corner case that where name dispatching stops working. Because in NDN there is a prefix match. So when suppose I have interest name /a, just one component, with also the can be prefix element, then that interest will go to the NDT entry determined by the hash of /a. But when the data comes back, the data name is AB1. It will go to the forwarding thread found in NDT entry of hash value of /a/b. And these two NDT entries could point to different forwarding threads, and then name dispatching no longer work in this case. So the solution is we introduce a hop by hop header field called the PIT token, and then we use that PIT token to associate interest and data. PIT token is an opaque token that encodes forwarding thread ID and the PIT entry index. Every outgoing interest needed to carry this PIT token. It is a 64-bit field in the link layer header, or in NDN, it's called NDN LP, and it's hop by hop. Then with the data and the NAC, when it comes back, the upstream node must put the same PIT token in the NDNLP header of data and the NAC. And then using the forwarding thread ID portion of the PIT token, it's here, the forwarding, so suppose PIT 1 forwarded the interest, the PIT token has forwarding thread ID, part is 1. It goes to upstream. When it comes back, the data also need to carry the same PIT token, including this forwarding thread ID. Then back in the input thread, it will be able to the input thread can look at that byte and see, oh, PIT 1 handles the interest, so we dispatch it to forwarding thread 1. The rest of PIT token is used for accelerating PIT lookup. It's used to accelerate PIT lookups, but it's not required for correctness. Then we go to the content store. So content store is a hash table, but in NDN we have to support a prefix match. One of the NDN design principles is in-network name discovery. The interest should be able to use incomplete names to retrieve data packets, but the hash table doesn't support only supports exact match. It doesn't support prefix match. So our solution is introducing indirect entrance. So this here is an example. Suppose I send the interest AB, but the data come back is called AB1. In this case, I am going to insert 2 entrances to the CS. The AB1, this AB1 it is the data name entry, and then this is called a direct entry, and it carries the data packet. I also insert an indirect entry called AB. AB is named after the interest. So the assumption is when consumers want to use name discovery, it will be using the same interest name to do name discovery. So if the consumer want to find it, usually the consumer will always send the interest name AB. It's not going to send the /A. And in that case, when the next interest is named either AB1 or AB, it can find this CS entry because it's in the hash table. But in case the next interest name is /A, it cannot find it. It has to be sent to the producer. But I hope this does not happen because that's an assumption. Okay, go back to the input thread. So we are using some of the hardware offloads supported by the Ethernet adapters. But today, most Ethernet adapters only support ISS rules, receive side scaling rules that matching on Ethernet and IP header fields. And so far, I have been using it to support creating multiple phases on the same Ethernet adapter and distinguished by the MAC address. The preliminary benchmark shows that when I have more than 8 forwarding threads, the input thread becomes a bottleneck. And also, if the server machine has 2 CPU, 2 NUMA sockets, and the traffic need to cross the NUMA boundary, it will reduce throughput by between 12 and 25%. So, but the current ISS rules are not powerful enough for eliminating this bottleneck. So we need better ISS rules. I also found that some NICs, they support eBPF and FPGA, but the products are very limited. And the development cost is quite high, especially for FPGA. Basically, each chip needs separate development efforts. But what I wish that the Ethernet adapter could support in the dispatching, in the filtering functionality is first, I hope they can match or offset into the data portion of the Ethernet frame. If I can get that feature, I will be able to distinguish interest versus data. And then in case the packet is a data, I can also use the hardware to read the first octet or the forwarding thread ID portion of the PIT token. Then I can place the data straight to the forwarding thread on the correct NUMA socket. So there is somewhat fewer NUMA crossing when it's being forwarded. But implication is this could need minor changes to the hop-by-hop header fields, but it does not affect the network layer at all. And also, I wish the NIC can support randomly dispatching to multiple queues, so that I can use more than one input thread to decode and process interest from the same NIC in parallel. But ultimately, I hope NIC can the Ethernet adapter can understand some of the NDN semantics, but that's 10 years from now or more than that. Next up is the support for implicit digest. Implicit digest is an NDN protocol feature. It allows the final component of interest to be the SHA-256 digest of the whole data packet. And the forwarder will need to do digest computation on the data packet in order to determine whether the interest with implicit digest could be satisfied. But digest computation is slower than all the regular forwarding workloads. So I cannot really do that in the forwarding thread. So the solution is introducing a crypto helper thread. When the forwarding thread receives the interest or a data and it determines that the digest computation is necessary, it will pass that packet to the crypto helper thread, ask the crypto helper thread to compute the digest. Then forwarding thread can continue with the next packet. Then in the crypto helper thread, it will invoke the DPDK crypto device. It could be software like OpenSSL, or it could be hardware like Interim Quick Assist. The crypto device will compute the digest, and then the packet comes back to crypto helper thread, and then we use the normal dispatching method such as NDT or PIT token to redispatch the packet to the forwarding thread. And the forwarding thread can process this packet again, and with the digest already carried in its metadata. NDN DPDK also supports the forwarding hint. Forwarding hint is a routing scalability solution. In the example up there, the interest name is unroutable but the forwarding hint can have one or more routable names. Then in the forwarding thread, we will look up the fib first with each of the forward delegation names in the forwarding hint. Then the first delegation name found in the fib is called the chosen forwarding hint. Then we can forward the interest according to that fib entry. And also interest with different chosen forwarding hint cannot be aggregated in the PIT. This is to avoid the scenario similar to cache poisoning. And then for the data will be matched to the PIT entry using the PIT token. So I know which forwarding hint brought back the data because of the PIT token. And also to prevent cache poisoning, content store of each chosen forwarding hint is also logically isolated. So if two interests with different chosen forwarding hints, they cannot aggregate, they cannot be satisfied by cache at all. Finally, I have some ideas for reflective forwarding. It does not mean I committed to do it. It's just if I am to implement reflective forwarding in my forward architecture, what I would do. First is the suggestion for the reflective forwarding draft says I need to update the fib from forwarding thread. But since I have RCU and I try to do RCU from forwarding thread, it would be too slow. So I think I should just skip the fib and use only the PIT to determine the forwarding path. Then I want the reflect interest to contain the PIT token of the original interest, but not in the name, it's in the forwarding hint. And this does mean that this forwarding hint, the PIT token in the forwarding hint will change hop by hop. But a benefit is the reflective interest and also the data packets, they can have normal names. They don't need the special name component in the front. They don't depend on consumer being able to generate good random numbers. And they don't require the original consumer to encapsulate the data if the original signature is important. Then in the forwarder, the input thread will the forwarder will be able to identify an interest is a reflexive interest because the forwarding hint start with a reflexive component, and then the input thread will dispatch with this forwarding hint instead of computing the hash of the interest name. Then for the forwarding thread, it will find the PIT entry of the original interest using this PIT token. And then it also needs to verify the current reflective interest matches the reflexive name in the original interest. and the original consumer did not prohibit further reflect interest from being forwarded. So here the blue one is the original interest data exchange, and the yellow one is reflexive. We can see the blue PIT token on the upstream side. Upstream will put the same PIT token in the forwarding hint. Okay, the last page is the references. Okay, thank you.
Okay, thank you very much. So there are a few questions already by Dave. So Dave, why don't you ask the question again?
Well, I'll take the second question offline, but the first one was, let's say I create an object /A/B/C/D//Z. So there's 25 name components. Does that mean if I want to enable prefix lookup, I need 25? One for each possible prefix that somebody might want to look it up by?
Are you talking about the CS?
Yeah.
That's not the case. It doesn't matter what your data name is, but I will only create one indirect entry, which is the interest name. I don't create them, I only create one.
Which one do I, let's say I have an object A, B, C, D, E, 25 name components, right?
What's the interest name that retrieved this object?
So I give an interest for, say, A/B as a prefix lookup.
I'm only able to look up if the second interest has the same name as the first interest. Otherwise, the CS will miss.
But then you're not doing prefix lookup.
In
other words, if I send an interest for A/B/C for this big long thing, and I have an A/B/C/D/E/.
Yes, this is a partial.
That should be returned, right? Because it matches.
Yes, but this cannot match because the assumption is the consumer should be using the same interest name to discover the data name.
No, you should be using a prefix of the data name to discover it.
But in reality, the application will be using the consistent prefix. Usually, the data name ends with an segment, and the consumer will use the name that without the last two components. So the name used by consumers is highly predictable.
Let's take it offline. This does not match my understanding of prefix lookup in NDN.
So Lisha says, it seems you can
Did we lose audio?
Yeah, something happened with
Seems like it,
Yeah,
sadly.
I did not hear any question.
Yes. So there's a discussion here on the WebEx chat, and so Lisha was asking, or was saying that you can just simply use forwarding hints to support the reflective forwarding function. And I was saying that yes, but then you have to accept the fact that both parties have to expose sortable names, and you can see the discussion in the chat here. So any more questions on the NDN DPDK forwarder? Okay, then thank you very much for doing this. Super interesting. So we move on to our last presentation, and that's Anil on their QoS approach for ICN. And I'll make you presenter. Just a second. And you have the floor.
Hi, hello everyone. So I'm Anil Jangam, and I, along with Prakash Sutar and Milan Stolik, we are presenting the QoS approach for the information-centric networks. And we have released, posted the last update, which is 0.2, and here are the updates of the changes. So what we have added is about the discussion of the network resources to be controlled, and mainly those are link, content store, and corporate memory, that is PIT, and the compute. In addition to that, we have also described some initial points on how the QoS treatment types are going to be and what network resources they influence. And some of this work is having some overlap with the QoS work that is done for the IoT by Senk's team, and we have referred to their work as well, and as well as Dave has also published his QoS architecture draft, and we have a lot of feedback also received from Dave, which we have incorporated here. In addition to that, we have introduced the QoS marker into an hop-by-hop header. Our initial or the 0.1 draft was talking about QoS marker as a name-based encoding, and we received some constructive feedback from Dave about some of the potential challenges involved with that approach. So we have another option using hop-by-hop header, and then depending on the feedback from the community and some of the experiments that we are doing, we will decide which way is the more better and or advantageous. Then we have the improved PIT scaling design, in which case the marker state information is now stored as part of the interface rather than as an explicit entry. So this will help to reduce some of the PIT load that is going to create, and I'll explain a couple of use cases what I mean by that. And we talk about some introduction to the QoS remarking scheme. So we had discussed about this in the initial presentations, and then we will make it more explicit now, and then especially by hop-by-hop header encoding, the remarking scheme is feasible now. And finally, we have some editorial improvements made in this draft as per the feedback we received. I'm not able to move. So this table summarizes the QoS treatment types and the network resources that influence. And so this has some overlap with the work done by the IoT team. And here we define the resource type as a link capacity, the content store capacity, the forwarder memory, essentially PIT, and compute capacity. And the ++ sign here kind of indicates there's an increased resource as far as that particular type of treatment is concerned. So let's say in reliable delivery, we need more CPU utilization, or there will be more queue utilization and cache utilization and so on. So and then various other treatment types listed here will have the corresponding. I mean, this is again initial projection. We are working on some of the experiments where we will have more clear data or understanding. And in typical case, the QoS modeling or the treatment modeling is the trade-off of things where the ability of handling number of traffic classes given the total amount of memory we have, let's say on the PIT or in the cache, and the processing capacity. And the second is the trade-off between the ability to express the type of QoS treatment given the protocol encoding ability and the algorithmic implementation. So now what we have seen in traditional IP world is, we have only limited TSCP codes, whereas in NDN we can have more space to encode the QoS treatment. Now, whether we need just, let's say 6 digits or more, let's say 1 byte or 2 byte, it depends on like how expressive the QoS treatment can be, and then that is where the TLV based approach is more providing more opportunities. This is the proposed design for the TLV encoding for the hub based QoS mark, and we introduced it as we would like to introduce as a mandatory hop by hop header, just to make the semantic of this header that it has to be forwarded by every router to the next hop, so that every the downstream router has the opportunity to see what the QoS treatment is intended by the original consumer, and then it acts on it. And right now we are proposing it as a 1 byte field, which is like 8-bit QoS field, and depending on the type of treatments and then combinations, we will see whether one byte is enough, or how we can break it, or maybe make a use of 2 bytes and so on, so that we don't have final clarity on that as yet. Moving to the next slide. In the QoS over forwarded design, or the PID design, as we said earlier in the original draft, we were having an explicit entry for every QoS marked or duplicate interest with having different QoS markers. Now we have changed it to interface based state setting. So the QoS marker will be saved as part of the interest data structure rather than the explicit PID entry. And the interface data structure, it can be enhanced to save the QoS marker. And there are 2 use cases which we already documented in our previous submission, but just for the sake of completeness with the newer design of this interest in the PID, I'm just reiterating those 2 use cases here. And one is the case where we receive duplicate interest with higher QoS markers and received on the same interface. And I'll explain how this is possible. And the second use about receive interest. So when I say duplicate interest, is the interest with the same content name, and the second interest that is received having the highest or the QoS marker, but received on a different interface. Now look at this PID entries. The interest 1 is received on, both are received on phase 1, but one is the interest 1 is having the QoS marker 1 and QoS marker 2, and the QoS marker 2 is the high priority interest compared to the QoS marker 1. So in this case, we will be forwarding the second interest as well, and this is where the PID aggregation relaxation is going to take place. This is going away from the well-known aggregation mechanism of the PID here, but this is I don't want to call it as a limitation, but this is the price maybe we will have to pay for the implementation of the QoS, because this is a possibility. Now, and the only the other aspect is that only interest with lower QoS marking will be aggregated. But if some interest comes with a higher priority, then that will be forwarded, even though a pending interest is already exists, but with a QoS lower QoS marking. And as far as that QoS data delivery at PID is concerned, the data delivery will be handled based on the QoS marker state that was saved into the PID. So we don't have to have the the QoS treatment which was like going to the upstream routers using through an interest that need not come back into the data packet. So that one change that is we are doing here. So the PID entry in QoS marker, depending on which interface that was received, if it is the packet data for data packet was forwarded on the downstream interface with the highest QoS marking recorded, at the interface, then it will go with the data packet will go back to the downstream router on using the higher QoS marker. And in case 2, if data packet is forwarded on the downstream interface with the actual QoS marking recorded at the each interface. So now this is the case where the same content is having 2 different entries, and this is where that relaxation of bit aggregation case that I talked about in the previous slide. And finally, in the which I think I have not mentioned about it, but the remarking case of which I mentioned in the initial slide, the QoS remarking scheme, where traditionally what is happening, at the AS boundary or the administrative domain boundary, or maybe between 2 routers, if router decides to remark the QoS for whatever reason, the upstream router now doesn't have the track or the knowledge about what was the original QoS that intended by the consumer. So it is always working based on the previous router's projection or the remarking case. So in the remarking, the original QoS marker is also preserved, as well as the intermediate router can now remark it and then still forward both the QoS markers to the next router, so that the next router can decide whether based on the remark QoS or based on the original intention. So that's the final change that we are talking about. And so we will discuss more about this remarking scheme as well as the protocol encoding into our next submission. So we are looking for the more feedback and more comments from the group. So far, we have received good amount of comment, very constructive feedback from Dave, which we have incorporated into this work. And now Luca has also agreed to review this draft, and we will take it from there. Thank you.
Okay, great. Thank you very much, Anil and co-authors, for continuing this work. Yeah, so it seems, yeah, are there any questions? Yeah, I don't see any. So it seems that the draft has been getting some feedback, and so there has been some discussion on the mail list. So it would be great if we could continue this. And so in general, the whole QoS topic is, of course, really interesting. And so I think we have kind of seen that there are different approaches, and yeah, let's continue working on the technical work in the group here. Thanks again.
Just a quick injection here. I noticed a bunch of people have already signed up for reviews on this Google sheet. So I'm encouraged it may actually be working. And thank you, all of you who volunteered to do reviews.
Okay, yeah, this brings us to the end of our agenda. Just 2 quick comments. So as we have seen today, it's kind of doable to hold meetings like this using online tools, but we shouldn't kind of only use WebEx. So we still have our mail list, so please really use that. I mean, we can get lots of useful work done. And then, as Dave said, please help with the draft reviews and yeah, and kind of improve the technical quality of the work and keep our documents evolving. With respect to future meetings, well, as you probably noticed, it's a bit unpredictable what's going to happen. So we could imagine that there's at least one other online meeting we're going to hold. But really, let's not wait for these synchronous meetings. So we can spin off new work on the mail list and a direct communication as well. So let's just keep doing that. Yeah, thanks for staying with us. Sorry for taking a bit longer. Please stay safe, everybody, and hope to hear you again soon. Bye-bye.
Bye, thank you.
Thank you. Bye.